The Michelson Morley experiment, one of the greatest duds in all of history, a null result that baffled everyone. So what was it? At the end of the 19th century, it was still cool to do experiments involving the Earth's motion around the sun. The Foucault pendulum was a fairly recent invention, and stellar parallax was just now being observed in nearby stars. Those are other stories, but that's the same sort of thing Michelson was after, some echo of the Earth's motion observable in this dusty basement. So, what was this experiment? How did it work? Why did it fail? And why should we care? That's what this video is about. The experiment itself was pretty cool. It involved a giant 30-foot-long granite slab suspended in a pool of mercury, and there was stuff on top of it too. That stuff was an interferometer, a way of measuring very small changes by splitting apart and then recombining a beam of light. More on that later. First, why suspend this thing in a pool of mercury? Well, that's easy, so it can rotate. Michelson expected different results from the interferometer when the experiment was conducted at different angles. But why? Because it doesn't just rotate. It's also flying through space on spaceship Earth. Here's one way to look at it. Consider starlight coming from the left and from the right. Because of the motion of the Earth, you'd expect the light from the left to have a higher relative speed. Got it? Again, this turns out to be wrong, and Michelson was not looking at starlight. But again, isn't this what you'd expect? Well, it would be if you thought the Earth was flying through a grid of ether. A grid of what? Ether. To ruin the punchline, it doesn't exist. But in the 1860s, James Clerk Maxwell showed that light is an electromagnetic wave. If sound waves travel through air, then what do light waves travel in? Ether. And with this, somebody's a little bit upset. They're thinking to themselves, what about the motion of the Milky Way galaxy? What about the expanding universe and relativity and all that? Well, those are 20th century ideas. This is the 1880s, and a grid of absolute space may seem quaint to us, but it was all they knew. So, how is this rotating interferometer supposed to show that the Earth is flying through ether without looking at starlight? By changing reference frames. Consider a, quote, ether wind. It's like the kind of, quote, wind that you would feel when you drive in a convertible. The interferometer was designed to show the effect of this wind on the light as it was turned to various angles. And that's what we'll try to explain. First, what does the interferometer do? It sends a beam of light through a half mirror, splitting the light and sending two beams in perpendicular directions. Direction is key. Those two beams then recombine inside the interferometer. More on that later. Right now we'll focus on the most important part of the trip, perpendicular directions, but a tie race. Now, what happens when we redo the experiment with an ether wind? We'll consider the horizontal motion first. Moving to the right, the light would be sped up. Moving back to the left, it would be slowed down. Imagine swimming with a current against a current. Would these two effects cancel out? The math says no. The windy trip takes longer. Think of it this way, time. The wind helps you for a smaller amount of time and is against you for a longer time. We'll get into the math in just a second. First, before we do that, the vertical path. Yes, I know it's not really vertical. Since we're now perpendicular to the wind, there's no effect, right? Wrong. You must swim, quote, upstream a little bit in both directions in order to make it directly to the mirror and back. And if you're uncomfortable with the light, quote, changing directions like this, revisit Huygens' principle, or just remember that it is really the mirrors that are moving on spaceship Earth. Final velocity with the ether wind can be found with the Pythagorean theorem. And again, the trip is slower with the wind. Putting it all together, the wind-free trips tie, they're the fastest. Then the vertical trip, that's a little bit slower. And then the horizontal path, that's the slowest. Even though they're all pretty close. Good thing we have an interferometer to measure these very small differences. Since we've already found all the velocities, calculating time is pretty easy. All we need is the size of the platform, and d equals vt. Again, we'll start with the horizontal trip. The time for the round trip is just these two guys added together. Try plugging in values for c and v if you don't believe me on this, but the time really is greater than L over c times 2. Now the vertical trip. Yeah, it's not really vertical. Anyway, this is a little bit more difficult, but notice that it's equal time going out and coming back. So that's nice. Our goal is to compare these two different windy trips, but we'll need to tweak the equations just a little bit. A warning, this is not for the faint of heart. And believe it, or not, our goal here is to simplify these expressions. Yeah, these expressions with this guy, gamma. Now wait a minute, I've seen you before. You're the Lorentz contraction factor, the factor that stretches and shrinks space and time for Einstein's relativity. Yes, it's the same gamma, but this is totally different physics. Historically speaking, Lorentz's contraction predated the relativity which made it famous. History is funny. But enough history, more simplification. That's pretty good. Now we can find the change in time. Plugging in. The distributive property. Distributive property again. Stuck. We need help. And what makes this gamma term interesting anyway? The binomial expansion. Who could have guessed that? Math. Now for our purposes, this first term, that's what we're most interested in. So goodbye, gamma. Prepare to be substituted for. And I was just getting used to that guy. Stay calm. Now what? Underline. What does that mean? It means you're going away. Can we just do that? Can we just pretend that this term doesn't exist? Yes, we can, because he is essentially equal to 1. Our expected ether wind velocity is much less than the speed of light, so you're equal to 1. See ya. And we're done. That's our expression for the difference in time. With this equation and the results from the interferometer, Michelson was finally ready to find the speed of the ether wind. What would it be? Well, let's find out, and we're going to start by guessing that the ether wind is 30,000 meters per second, and that is not a random guess. It's a rough value for the calculated speed of the Earth moving around the Sun. We know the orbital distance of the Earth around the Sun and the orbital period. Of course, it's pretty fast. But look at that equation. It's got a c cubed term, and that's pretty scary. Oh, and I can see why they wanted a big platform now. They wanted L to be big. That's nice. What value would you get for delta t? 10 to the negative 16 seconds. That's really small. And if you're uncomfortable with the binomial substitution and the reducing and all those gimmicks that we used, go back, be my guest. Scroll back, go back earlier in the video and try to plug this into the other expression, see what you get. But 10 to the negative 16 seconds, I don't have a good enough stopwatch for that. Well, turns out we do. The interferometer. Well, let's look at it this way. Assuming a constant wavelength and frequency for the light wave, this is the difference in, quote, distance that the two waves would go fighting against the wind. Well, wait a minute. Are you just assuming that light travels at a constant speed? Well, kind of, but we are too close to the end to stop now. The distance is still small. That's really small distance, but it is a large fraction of the wavelength of visible light. And that means when these two beams recombine inside the interferometer, we should get a noticeable, measurable diffraction pattern. The two waves should be a little bit out of phase. They should have been, but they weren't. No matter what rotational angle they tried, the two waves matched up perfectly. And in a way, this is a very elegant experiment. Test the light, rotate the disk, test it again, and again, they expected different patterns from different angles, but never found any. It's almost like they really did measure the velocity of the ether wind, and they measured it to be 0. Like I said, a baffling null result. It's almost like absolute space doesn't even exist. Or maybe did they interpret the math incorrectly? I don't know, but we are here at the dawn of modern physics. Relativity and quantum mechanics are coming. And you could say that quantum physics and relativity came to mess up the tidy Newtonian world of classical physics. Or you could look at it this way. Modern physics came to rescue us from this mystery by giving us many more.